Millikan's oil drop experiment. Millikan wanted to find the charge of an electron. We all know the charge of an electron is 1.602 into 10 to the power minus 19 coulomb. Okay, what is the experiment he did to find out the value of E, that is 1.602 into 10 power minus 19 coulomb, is what is this question. Okay, so what is the idea behind, or what is basically the principle behind? Guys, if I have to make you understand the principle, let me get into the diagram part of it. Okay, so here we go. Say suppose I have two discs like this. Okay, one disc which is perforated, which has a hole on the top, another disc which is there on the bottom. Okay, I'm going to call the perforated disc as A, the other disc as B. And let the distance between these two be very small as in it's going to be simply 16 millimeter. Okay, and the diameter of this disc, it's 22 centimeter. It's big compared to the distance. Say suppose what I do is I make the name of the, like as the name of the experiment says, I make an oil drop to fall. Okay, so let me have a container having oil drop. Okay, though it is said as oil drop, the liquid that we're going to make use of is glycerin. Glycerin is that oil that we are making use of, with the help of an atomizer which can make droplets to fall. Okay, say suppose some drops are falling down from the top through this hole. Okay, so what is the principle behind Millikan's oil drop experiment? Very simple. Any object which falls from a height, it freely falls due to gravity. Obvious. So this oil drop, which is now going to be called as uncharged oil drop, as we are doing nothing to it, it is an uncharged oil drop, it freely falls due to gravity. Okay, now by some mechanism, what is the mechanism? Say I gonna pass on X-rays or ionizing radiations. They're gonna ionize the gas inside, air inside, which is gonna get split into pluses and minuses. Say suppose some of the minuses, that is the electrons, got picked up by an oil drop. Some charged electrons got picked up by an oil drop. Can I call this oil drop now as a charged oil drop? Yeah. Now, what if I keep electric field here, say minus here and plus here? Oh, a minus can repel a minus? Yeah. So the charged oil drop now can be repelled by this electric potential or electric field that we are supplied. Oh, such a way that the speed or the velocity with which the oil drop is falling down can be controlled. Okay, how can we going to control? We're going to increase the value of this negative potential here in such a way that it repels the negatively charged oil drop in such a way that the oil drop slows down with the velocity with which it is traveling down, as well as it can even make the oil drop to move up because of repulsion, or for a particular amount of time we can even make it to stand in air in between these two plates. This is the principle behind. So now we can talk about the principle behind the experiment. So it's very simple. Millikan's oil drop experiment says the principle is motion of uncharged oil drop under free fall due to gravity and charged oil drop in a uniform electric field. By adjusting the electric field, charged oil drop can be made to move up or down or even kept balanced in the field. You can see it in the book. As I told you, the experimental setup is this. This is the rough diagram. In fact, this diagram would do. So as you guys know, there are going to be two discs A and B. One is perforated. The diameter of the discs are 22 centimeter each, and the distance between the two discs is 16 millimeter. The liquid that we're going to consider is glycerin. Why glycerin? Glycerin is a viscous liquid. If I make water to pour down from a bottle, it will pour off very fast. Same time, like think about ketchup, it will flow down very slowly. Same way, glycerin is also being a highly dense or viscous liquid, it also can fall off slowly. That's why I have taken glycerin. So this can be contained inside a chamber, and if you have to view it, maybe via a light source from here or through a spectrometer, you can view. Diagram looks messed up, right? It's okay, I know you would have understood it. Otherwise, go and have a look at the book, the diagrams there. Okay, now as the experiment was told by the principal, let's talk about the motion under gravity. Okay, the oil drop, that uncharged oil drop previously, falls down definitely with a force, right? Yeah, force is nothing but mass into acceleration. So F is equal to ma. Yeah, we know density is equal to mass by volume. Therefore, mass can be written as density into volume. Let the density of the oil drop be called rho. Volume being taken the form of a sphere, the volume of a sphere is 4 by 3 pi a cube, a being the radius of the oil drop. So instead of mass, I can write 4 by 3 pi a cube into rho, and instead of F, now I have to write mass into, so 4 by 3 pi a cube into rho into acceleration. Due to gravity, I'm going to call it as mg, so it is g. This is the force with which, or this is the weight with which the oil drop is falling down. When the oil drop falls down, obviously there will be an upward thrust experienced by the oil drop. Why? Because there is air. Okay, so the air also will take the shape of the oil drop. So I'm going to say that the upward thrust by air is 4 by 3 pi a cube, density of air sigma into g. Oh, so what is the net downward force? Net downward force is nothing but 4 by 3 pi a cube rho g, with which it is falling down, minus 4 by 3 pi a cube sigma g. Taking 4 by 3 pi a cube g common outside, it is rho minus sigma. This is the net downward force with which the oil drop is falling down. Okay. When the oil drop falls down, let us consider that it has attained a terminal velocity, a constant velocity called v, with which it is falling down. Now, we know by Stokes' law, okay, in 11th standard you should have learned this. By Stokes' law, the viscous force will be 6 pi eta a v, which will act on the oil drop. Oh, so the net downward force 4 by 3 pi a cube g into rho minus sigma is now equal to 6 pi eta a v. Take a and cancel out here, I get pi also gets cancelled out. So a square is equal to 6 eta v into cross multiply 3y 4 g into rho minus sigma, or if I just cancel out this 2 3, So it is totally 9 eta v by, right? Okay, let me write it. A square is equal to 9 eta v by 2g into rho minus sigma. Therefore, A is equal to 9 eta v by 2 into rho minus sigma times g the whole to the power half. This is the uncharged oil drop. Now that we have found out the radius of the uncharged oil drop, let's talk about the motion under electric field. I want to get back to the diagram again. I even want to draw it one more time. Okay, you guys remember, within a chamber there were these two discs. One was hold, other one was there. The distance between them was 16 millimeter. The diameter was 22 centimeter. With the help of an atomizer, tried passing on some glycerin oil drop. We passed on X-rays, which ionized the gas, because of which the uncharged oil drop became a charged oil drop, carrying some minus charges, negative charges. We supplied some potential, remember I told you? Yeah, it was 10,000 volt of potential difference through a battery. Through a spectrometer, pass on light, and we'll also have a micrometer scale reading, okay, which wants to measure exactly the time taken for moving up and down, with which we can calculate the downward velocity, terminal velocity called v, and because of the negative potential, we can even make the oil drop to move upwards with the terminal velocity, say v1. If due to acceleration due to gravity, if it falls down with a velocity v, and because of that electric field that you have applied, it is going to travel with a velocity of v1 up. Okay, now let's talk on it. The force due to electric field, okay, EQ, is actually responsible for not only to balance the oil drop which fell down, but also is responsible for moving it upwards. Yeah, so what was the weight, net downward force with which it was falling down? 4 by 3 pi a cube rho minus sigma into g. Remember, not simply balancing that, but it also makes oil drop to move upwards. There were, as I told you already, there will always be a viscous force acting against anything which is moving, according to Stokes' law. Oh, this time as it is moving with a terminal velocity of v1 up, I have to write it like this. Okay, of which what do we know about this thing? This is nothing but our 6 pi eta av, yeah, downward force, yeah, plus 6 pi, now it is eta av1, which is EQ. Taking 6 pi eta a and all outside, is going to be v plus v1, which is EQ. We all know the value of a. Just some time back we found out the value of a, right? I'm going to substitute that. So EQ is equal to 6 pi eta. In the place of a, I can substitute this, right? 9 eta v by, yeah, 9 eta v by 2 times rho minus sigma g the whole power half into v plus v1 now. Okay, eta power half, there is already an eta outside, so put together I can write it as eta power 3 by 2, yeah. So I can bring this alone outside and make it as 6 pi eta power 3 by 2 into 9, v will be inside, 2 times rho minus sigma into g power half into V plus V1. This is EQ. We know that E is equal to V by D. Knowing the value of V, remember 10,000 volt. The distance between the two plates, remember 16 millimeter. We can actually calculate the value of E, I mean to say, with the help of which we can calculate Q. We also know Q is equal to NE. If you are calculating Q, it will be an integral multiple of E, out of which if you are trying to find out the value of E, it will be 1.60 to 10 power minus 90. Cool. This is what is the charge of an electron found by Millikans. Thank you.